Hi everyone, this is worksheet 6.1, Heisenberg Uncertainty Principle example. And on this worksheet, I'm going to work through how the Heisenberg Uncertainty Principle is valid for a given wave function in a specific example. Okay, so recall that the Heisenberg Uncertainty Principle involves the standard deviations of position and momentum. And remember that if we've got the standard deviation of some observable A, this is equal to the square root of the average of A squared minus the average of A squared. All right, and remember that the average of A is going to be the integral of the complex conjugate of the wave function with the observable's operator in there times the wave function integrated over space. And that the average of the observable squared is the integral, the complex conjugate of the wave function, and then the operator acting on the operator again, wave function dx, like that. Okay, so the example that we're going to consider, or at least verify the Heisenberg uncertainty principle with, is an example from chapter 3 where the wave function is equal to some normalization constant and then little a squared minus x squared. And this will be true if x is in between negative a and positive a, and it will equal 0 otherwise. So what does this function look like? This function goes from negative a to positive a, and it's going to form a parabola shape like this, and then it's going to be 0 all along the axes like that. All right, and in chapter 3, you'll find in the lecture notes, we actually normalized this particular wave function, and we found that a is equal to the square root of 15 over 16 little a to the 5th power. Okay, so in order to verify the Heisenberg uncertainty principle, we need to find the standard deviation of momentum and the standard deviation of position to see if the Heisenberg uncertainty principle is true. And remember that the Heisenberg uncertainty principle says that the standard deviation of momentum times the standard deviation of position is greater than or equal to h bar over 2. Okay, so if we need to find the standard deviation of position, this is going to be equal to the average of the position squared minus the average position squared. And similarly with momentum, like so. Now, if you go back to the lecture notes from chapter 3, you'll see that we've already computed the average position for this example, and it's 0. And we also computed the average momentum, and we saw that it was also 0. So, really all that we need to calculate are just these average observable squared. So let's get the average position squared first. All right, let's get this set up here. Average of x squared is going to be equal to negative infinity to positive infinity, eigenfunction squared, and then the position operator acting on itself, which is just going to be x squared, eigenfunction dx. And then let's write this out explicitly based on what we know about the function. We can integrate from negative a to a. We've got the normalization constant, a squared minus x squared times a squared minus x squared dx. Now, if you want to, go ahead and pause and give this integral a try if you'd like to. Otherwise, I'm just going to work it through right now. But feel free to pause and see if you can get the value of the position squared, the average value of the position squared yourself if you'd like. Okay, now I'm going to pull constants out to the front of the integral. Okay, so this all equals a squared. Integral from little a to negative little a to little a, x squared. A squared minus x squared squared dx. Okay, and then I'm going to FOIL this out. A to the fourth minus 2a squared x squared plus x to the fourth dx. Okay, this becomes a squared, just like before. Now I'm going to spread out and distribute that x squared among all the terms. So let's see what we get there. Squared minus 2 squared x to the fourth plus x to the sixth dx. Okay. And then I get the antiderivative of that. It becomes a squared. A to the fourth, x to the third divided by 3, minus 2, a squared, x to the fifth divided by 5, plus x to the seventh divided by 7. And this is from negative a to a. Okay, and now if you do all of the arithmetic, if you perform this, or if you plug in a and negative a into this antiderivative and you calculate out the result, what you will get is a squared, a to the seventh over 3, minus 4, a to the seventh over 5, plus 2, a to the seventh over 7. And then this becomes 16 over 105, once you add all those fractions together, times a squared, little a to the seventh. And we already know what big A is, so we can plug in the known value of big A in here, and we get 16 over 105. And this is times 15 sixteenths. Oops. A to the fifth times a to the seventh. And then when we further simplify that, we get a squared over 7. And that's it for the average squared position. Okay, so for this next step, we're going to need to find the average of the momentum squared. And to get that, this is just going to equal an integral from negative infinity to positive infinity, the complex conjugate of the wave function, and then the momentum operator acting on the momentum operator, which is going to be h bar over I, derivative with respect to x, of h bar over I, derivative with respect to x, of the wave function, dx. And then I can pull the h bars and the i's out of the integral and make things a little easier on myself, and I get negative h bar squared from negative infinity to positive infinity. Psi star, the second derivative of psi dx. All right, let's first get the second derivative of psi, and we know that psi is just a, big A, times little a squared minus x squared. I can pull the a out and get the first derivative. So getting rid of one of those derivatives, the a squared goes away, and I'm just left with negative 2x. And then I get the derivative again, and I just get negative 2a. All right, so coming back here to finding the average of the momentum squared, this equals negative h bar squared, integral from negative a to a, big A a squared minus x squared. That's the complex conjugate of the eigenfunction times our second derivative here, 2a dx. And I can pull out the negative 2 and the a squared, and I'm just left with 2h bar squared a squared, integral from negative a to a squared minus x squared dx. And then this is a fairly straightforward antiderivative. This just becomes 2h bar squared a squared x minus x to the third over 3, negative a to a, equals 2h bar squared. If you work out those boundaries, 2a to the third minus 3 halves a to the third, like so. Okay, this is going to become 8/3 h bar squared a squared a to the third. And then I plug in the value that I already know for big A, and I get 8/3 h bar squared, 15 over 16a to the fifth, a to the third. And this becomes 5 halves h bar squared over a squared. Okay, so now we're almost done here. We've got an expression for the standard deviation of position, which is going to be the square root of the average of x squared, which we calculated to be a squared over 7, and then minus the average position, which was just 0 squared, and this of course just equals a over the square root of 7. Now how about momentum? Momentum is going to be the square root of 5 halves h bar squared over a squared minus 0 squared for the average momentum. This equals the square root of 5 halves times h bar over a. Right. So now, back to the Heisenberg Uncertainty Principle. The standard deviation of position times standard deviation of momentum. If we multiply these two things together, we get a square root of 5/14 times h bar, which is approximately 0.598 times h bar. And as you can see, this is greater than h bar over 2. So therefore, the Heisenberg Uncertainty Principle is satisfied in this case, as it will be in every case, no matter which wave function you choose.